All right, welcome everybody. So in this video, I want to take a step back and more generally define what we mean by a least squares solution. And then we can connect it back to the example that we've been thinking about where we were trying to predict the GDP per capita of a country based on a couple of predictors like life expectancy and literacy rate of people in the country. So let's let A denote a matrix M by N. And I'm going to call A model matrix because in practice, A is a matrix that contains the observed values of all of our predictor variables. And this value M, then the number of rows of this matrix are how many observations we had. We were thinking about a matrix that had 3 observations, 3 rows, and N is denoting the number of predictor variables that we have. So in the previous case, we had a 3x2 matrix because we made 3 observations, and each observation entailed recording 2 values, the literacy rate and the life expectancy. And then let's consider the vector y hat, which is a vector of the predicted response variables. So these are going to be all of our predicted GDP per capita. Okay, then the least squares solution of the equation A times beta hat. And now this is a vector of coefficients. And this vector beta hat should have as many coefficients as our model has predictors. So we have n different betas. And so a least squares solution to this equation, A beta hat equals y hat equals our prediction, is going to be a vector of estimates for the regression coefficient. So we're going to try and solve for each of these coefficients, beta 1, beta 2, up to beta n, such that this inequality is satisfied for all beta in Rn. So let me kind of break this inequality apart since this is the meat of the theorem. So on the left side, we have the length of y. This is a vector y of all of our observed response variables. So this would be all of the observed GDP per capita minus this vector A times beta hat is giving us the vector of predictors. So here what we are going to calculate when I take the difference of these two vectors, we're going to get the error in each prediction. So we want all of these errors to be, we want beta hat to be chosen so that these errors are as small as possible. So in other words, the errors are smaller than if we would have chosen any other combination of coefficients. And so let's take a look at the picture down below. So the different ingredients that we have here is y are the actual values. So these are the dots that I've plotted over here. So generally, our samples have many observations. We just had 3, but here's a picture of where you might have had like 20 different observations. This A beta hat, these are the predicted values, and these values are sitting in this subspace that's spanned by the column space of our model matrix. So here we have some subspace. We have an actual value which is not in the subspace, and we can picture the predicted value of y as the projection onto this subspace. So our predicted values are vectors in this plane, and this difference that we have of y minus the prediction is going to give us exactly this complement to the orthogonal projection. So that are these distances here are exactly the errors. So we want to minimize all of these errors. So we want to find values for beta 1, beta 2, up to beta n, so that these errors are as small as possible. That's the goal. So let's set up the corresponding equations that we're going to need to solve to find the least squares solution. So we want to minimize this difference of the response, the observed response y vector, minus the vector of predictions. So that's y minus y hat. And when we take this difference, we get these vertical distances over here, which we can write as the length of epsilon. That's this vector right here. But this is a vector of errors. So for example, maybe E1 is this distance right here, E2 is this distance over here, E3 is this distance. I'm saying E's, I mean epsilon 1, epsilon 2, epsilon 3, and so on. So we want to minimize the length of the vector of epsilons. And so that would look like taking the square root of the sum of the epsilons squared. So that's why we call this a least squares solution. We want to make the square root of all of the sum of the epsilon squares as small as possible. So the beta hat values that make these errors, the sum of the squares of all of these errors as small as possible, that's what we're going to consider our best fitting model. So for now, I just want to motivate what these least squares solutions are and why that is connected to finding us, for example, like the best fitting regression model for a set of observed data.